Okay, let's kick it off. Good morning, everybody, and thank you for joining us. In today's session, Shahryar is going to take us through some information and insights on how to efficiently electrify our residential building heating systems with heat pumps. Before we get started, a few things to note. We are recording this session. The recording and a PDF copy of the presentation will be available on the Save on Energy website in 1 to 2 weeks. There will be links that will be shared with you as well. You can also visit saveonenergy.ca/training and support to browse all of our past webinars and other resources that we have, like fact sheets, guides, and tools. My name is Megan Murray, and as I said, please just remain muted during the session, but if you do want to ask a question, we encourage you to use the chat feature or simply raise your hand. We have quite a bit of content to get through today, and we will do it as quickly as possible while reserving some time at the end for Q&A. With that, I'm going to hand it over to Shahryar.
Okay. Hello, everyone, and welcome to this session. As Megan said, that we are going to talk about the electrification of the residential buildings by heat pumps. The main purpose, for sure, it's going to be heating. We live in a cold climate, but yeah, it will cover the cooling purposes that our residential sector also needs as well. So let me go through the slides. So this is a high-level agenda for today. We want to see an overview of the heat pump technology. I'm sure that everyone knows about that one. We just quickly and briefly review that one. We want to see typical retrofit opportunities for single family houses and townhouses, and also social housing, and also multi-unit residential building as well. We will chat about the fuel switching versus the hybrid solution, because sometimes we need to do that one. And then, at the end, we look at the business cases and the financial side of these heat pump installation in the residential sector, and a few tips about working with the contractors and how to manage basically a project within the residential sector actually. So let's get started, and let's look at what are the typical space conditioning system for a residential building. If you live in a I would say in a house, in a single family house, or in a townhouses, typically we have systems like this. We have an outdoor unit actually, which is our air conditioning system, and then we have an indoor blower plus the furnace, which provides us the heating actually. In a multi-unit residential buildings, we have these stacked, I would say, systems, which each condo, they have their own system, and then the heating and cooling supplied by these pipes actually from a main central plant that exists there, either is from boiler or from a chiller, and then each unit gets the cooling and heating which is needed. So typical, I would say, heating and cooling, furnaces, boilers. We have a few boilers, in Ontario, as far as I know. Heat pumps are getting into the market, and that's a discussion for today. We have, some areas that they use electric baseboard heaters as well. For cooling purposes, we have, central AC or air conditioning system, the ductless mini split, air conditioner as well. And then combined system, which also is going to be the heat pump. Let's look at the heating system, the residential heating system energy sources that we have across the Canada and Ontario. So if you look at, first of all, in Canada, you see that most of the country actually uses natural gas. And then the second after that is going to be electricity. So that's a source for heating. And then a little bit of the fuel oil and also propane. So that's the general about the Canada. But let's look at the Ontario. So this is Ontario. Ontario is even more. So in Ontario, we use more natural gas for heating purposes, and a little bit of, I would say, electricity. Oil is very, very limited actually in here, and not much. And then propane. So yeah, I travel to the northern part of Ontario. There are some cities actually they use propane for heating purposes where those places that they don't have access to the natural gas. So this is our today's situation in Ontario and in Canada, and the goal is that to reduce that natural gas consumption and move it toward an energy efficient system actually. So I mean, looking at the heat pump system, these are the benefits of using a heat pump. The first and the most important one is energy efficiency. I will show you some basic numbers of why the heat pumps are more energy efficient actually uh, after this slide. But there are other benefits of installing the heat pumps as well. A heat pump can provide both heating and cooling, and offering a year-round actually comfort with a single system. That's a good one. It has environmental benefits, which reduces the greenhouse gas emissions actually, and especially in Ontario, we have a green electricity. So that's thanks to OPG, ISO, and all the energy generation or electricity generation in Ontario, we have a green electricity. So we should benefit from that one. And when it's better, maybe we switch from fossil fuel burning heating systems to electricity, which is very green. Its safety also is very important. The heat pumps, they don't burn any fuel on site actually, so it's very safe to have them inside our homes and our buildings actually. So it's safe for children and elderly residents as well. So those things that can happen with the other fossil fuel burning systems. Comfort is much better with these heat pumps as well. So the heat pumps provide a consistent heating and cooling throughout the buildings and maintaining a more stable indoor temperature actually compared to the traditional conventional systems that they fluctuate the temperatures actually. They have a longer lifespan actually, so that's the another benefit of having the heat pumps. And also the other benefit is the zoned heating and cooling. These days, that if we have a large house or if we have a large area and we don't want to cool down some areas and we don't want to heat up some areas and then but we can't do it with the existing systems. When it's on, it's gonna heat up everywhere or cool down everywhere. Yeah, we can go and close the registers, but again, it doesn't work. But with these um, heat pump systems, we are able to do that one actually. I want to show you this one. This is a very interesting. I want to show you some numbers and looking at why the heat pumps are more efficient than all other systems that we have for heating and cooling. Let's assume that we have a house and we want to keep this house at 20 degrees Celsius. So that's our indoor temperature set point that we want to have it on a thermostat. Let's assume that the temperature outside is -2 degrees Celsius. Thanks God, I mean, this week is super hot. It's good actually, but the winter is coming soon. So it's going to be -2 degrees Celsius outside. Based on the evaluation, this building requires 80,000 kilojoule per hour, which is equal to 75,000 BTU per hour or 22 kilowatt or 6.3 ton actually of the heating. If we want to go straightforward and um, install a heating system for this building, the first option will be a resistance heater, actually. So if we want to have a resistance heater, this is the amount of the heating that we have to supply, 22 kilowatt, because their efficiency, is 100%. So that's the good one to have it. So then we can go with the baseboard heaters, for example, and then use that one actually. We need to supply 22 kilowatts actually. If we want to use a natural gas furnace or a boiler, let's assume that we buy a good efficient one, which is its efficiency is 85%. So if we want to have that one, then we need 20 uh, 6 kilowatt actually. So we need a little bit more than this because those fossil fuel burning systems, they are inefficient because of that 15% inefficiency. So we need 26, a slightly lot, more than this 22 kilowatts. So that's the amount of energy or power we need to supply to this building to maintain its temperature at 20 degrees Celsius. But now let's look at the heat pump actually. So if we have a heat pump for the same condition with a coefficient of performance of 2.5, this is COP. I will define it later on, but this is similar to the efficiency for the natural gas boiler or furnace. So if we say that the efficiency or the COP of this heat pump is 2.5, means that we need to only supply 8.9 kilowatt power actually for this building actually. So this is the amount of heat that needs to be supplied to this building compared to 22 kilowatt, compared to let's say uh, the natural gas furnace or boiler, which was 26 kilowatt. Now we are almost 9 kilowatt. So this is the efficiency that we are talking about. And this is the reason that, it's better that we move on and we use this system. There are many countries right now in Europe, from day one, they decided actually not using fossil fuel, systems. Norway is the one of the best examples. They have oil, they have gas, they have everything similar to Canada. But from day one in Oslo, they said that no, we don't want it. We want to use a more efficient systems. Yes, the installation cost is higher, the capital cost in the beginning is higher, but at the end, if you look at the life cycle, it's much cheaper actually. And the why is cheaper? Because of this reason. Because it's just we need only 9 kilowatt versus 26 or 22 kilowatt for heating up this building actually. So some numbers from the statistics that available for us to taking a look at that one is that the heating energy used for the heating of the residential building, um, combined for both, residential, commercial, and institution building, is about 16% of the total energy that used in Canada. So 16% of our total energy goes to just, heating or space heating of our houses, our offices, our institution and buildings as well. And then, 13% of this energy related to the GHG emissions. If we look at the electricity, just looking at the electricity, we see an increase of 21% of the total electricity use within the homes actually from 2000 to 2020 actually. And this is an increase that we see actually because the people they're switching, for example, from oil burning systems actually to electric baseboard. So that's a one reason. The other reason is that we are seeing that the people are installing the heat pumps as well. But heat pumps, as you saw, it does not consume that much electricity compared to a baseboard, actually. I told you before, in Ontario, we have a low emission electricity, which means that less greenhouse gases are actually emitted per each unit of energy. So why not using this energy efficient and low emitting systems actually at the same time, which is a heat pump for our residential buildings. So that's the reason again we need to consider heat pumps for our residential buildings actually. If you look at these graphs actually, so let's look at the left-hand side one. So the total demand for the energy across the Ontario is around 3,000 petajoules actually. So, and then you see that 20% of that one goes to the residential sector actually. So 20% of that one is around 600 petajoules that goes to energy use of the buildings that we have actually. So, and then which is a residential building. So this is high. If you look at the GHG emissions of these buildings, so let's look at the building sector and how much in Ontario we have the GHG emissions. So you see that it's a fair amount of GHG emission coming out of our building sector actually. So again, this is another reason that we have to reduce our GHG emissions and our footprint that we have on our climate. Let's look at the heat pumps installed across the Canada. This is up to 2021 data actually. So up to 2021, this data published by Natural Resources Canada from the federal government. So if you look at the total residential building across the Canada actually, so you see that Ontario actually, which is the blue one, plays an important role in that one actually. And many households decided to choose actually heat pumps, and it's increasing. So this is an interesting fact that the people realize that This is high efficient, low emitting, and also safe device actually to be installed for heating and cooling purposes in our buildings actually. If you look at just the condos again across the Canada, you see that again Ontario is playing, the second, or maybe I would say that now is the first one that, in 2021 that they install actually heat pumps. So again, heat pumps are getting more and more attraction, and the people, they realize that this is a good system to be installed in our facilities. Let's look at briefly what is a heat pump and how it works actually. So a heat pump is a mechanical device actually that it works based on a refrigeration cycle, and what it does actually, it moves heat. That's it. So it's a very simple term that we can define it. It's a machine that it can move heat from one side, which is going to be inside, and outside. And the good thing with the heat pump is that we can switch the operation or the movement of the heat. So, for example, when the outside is cold, this device, which is our heat pump, take the warmth from outside air or the ground or the water source that we have outside of our buildings, and then bring it inside actually to the building to make our houses warmer. And when it's hot outside, similar to today, so now what it does actually, it takes the heat from inside of the building and then dump it outside. So this is the simple definition that we can bring for this machine actually. So, and what it uses actually, it uses electricity. So it's a very simple. So we need just an electrical line connected to this machine, and then we can benefit from having this. So in a cooling season, which is like a summer right now, uh, these heat pump acts like air conditioning that we have in our facilities actually. So basically, it takes the heat from inside of the building and then move the heat actually to outside. Thanks to this reversing valve, this is a next only extra, I would say, component that exists in a heat pump, which is different than air conditioning, is this reversing valve. So this reversing valve actually can switch these evaporator and condenser that we have in our system, which is our heat pump system actually. So for a winter season, this reversing valve actually gets switched and basically takes the heat and then dump it inside our building. So the direction of the heat transfer will be from the outside toward the inside. And this is the only component which is, added to our AC, I would say, and then our air conditioning system can become a heat pump. That's a simplified, version of that one actually. Let's look at what type of heat pumps that we have. The first and the most or commonly used one is the air-to-air split systems. What does it mean, air-to-air? Air means that on the outside, our outdoor unit, we are using air for cooling and heating, and in inside also it dumps again as air, so for heating and cooling of inside the building. So similar to this picture that you see here, we have an outdoor unit, and this outdoor unit connected to an indoor unit. And what is these lines? They are that's actually the refrigerant line that we have. And then we need an electricity also connected to our outdoor unit. And then that's it. This outdoor unit can provide us heating during the winter season and cooling during the summer season. So when we want to install it, we need to do the duct work because it's air inside. And also we need to bring the refrigerant piping and also some electrical wiring that we need to do that one actually. So this is a favorable installation, operation, and maintenance cost actually. So that's why everybody prefers to have these air-to-air split systems actually. So in the air-to-air split system, as I showed you in that slide for the heating and cooling, we have a heat exchanger coil, and then we have a compressor, we have a fan and motor that works. Uh, the other difference is that the fan or motor is not on the top, it can be on the sides of the heat pump. So that's another way that we can differentiate the heat pumps from air conditioning, because air conditioning is just one stop the heat, so it's gonna have this fan upward. But for these heat pumps, they are most of the time their fans is actually on their side actually. So this is the one of the components that I told you, the reversing valve, which is added to our air conditioning cycle that we have. So then it becomes a heat pump. The other thing is that we need during the winter season, we need the defrost controls as well. So we need a defrost system for our heat pumps as well. So these are the two extra components that is added to our heat pumps that they can operate during the winter season as well. So as I said, the outdoor unit rejects, indoor heat to outdoor for the summer season and also for the winter season. Now the outdoor unit becomes an evaporator and actually it extracts the heat and bring that heat to inside our buildings actually. So these are the major components. We talked about it. This is an additional one that I want to bring your attention to. So up to now, we said that we need a reversing valve. We need a defrost system and defrost control. And also we need a supplemental heat sources. I will talk about these supplemental or additional heat sources. This is for extreme cold conditions actually. Sometimes we don't need it, depends on the design and depends on the equipment or the heat pump that we purchase. How is the efficiency? What is the lowest temperature that it can work actually? Sometimes we need to have a hybrid system. So this is an extra component that needs to be added to an air-to-air split systems actually. The other types of heat pumps, they are mini split heat pumps actually. So you see that now we don't have a duct actually. So there are some buildings that they don't have a ducting actually in there, or because of the space or because of any design, they don't have a duct. So basically we have that outdoor unit and then just the refrigerant is connected to an indoor unit actually, and that indoor unit provides the air. So we saw some of these also as well, and this is good for later on, you will see that this provide a zone control comfort actually without doing a duct work. So in the buildings that we don't want to have a duct work or we don't have a duct work, these mini split heat pumps, they worked actually good. And then we need to just run refrigerant line and then that's it. And that refrigerant line can be wall mounted, can be floor mounted, and in a drop ceiling or anywhere else actually. And this is good for a special space that we want to heat up or cool down actually. And it not just needs electricity. When we go to the larger systems that we want or larger buildings that we want to have, then maybe it's better to consider packaged heat pumps. So these packaged heat pumps or self-contained heat pumps actually they have all the indoor and outdoor components in them actually. So basically they can be installed and then we can connect a ductwork. Both ductwork can be horizontally or vertically, and we can install them on the ground level on a concrete pad or other places like a roof of the building as well. So one example is that we use a rooftop unit. So this is a one package unit that it includes a heat pump in it actually, and then it can run and then it can operate similar to what I showed you as a cycle, and then it can be connected by the ducts or other systems. We can add more efficiency to these larger rooftop units by adding air cool chillers as well if we require more cooling. So then probably it's better that we connect them also to an air cooled chiller and then use that one as well. So we can expand the system as it's needed. So it can be packaged in one, and then if we require actually more heating or cooling, then we can add more supplement to that one actually. The other types of packaged terminal heat pumps actually they are similar to this one that you see in the picture. Again, these ones we don't need even to run any refrigerant lines as well. Everything is inside of these packaged terminal heat pump actually, and it's self-contained. Everything we just need to plug it in to electricity and it's good to go actually. We turn it on, it has its control, it has its own heat pump cycle in it. It has an air blower and everything else as well. And then it can be installed, for example, under the window or wherever that we like to have it. So again, this is another types of the air source heat pumps actually. So these are the air source heat pump, again, air to air heat pumps that we can have. One new topic that I want to bring your attention is about the water source heat pump. Water source means that we use water actually instead of outdoor air for cooling and heating purposes. Why water is good actually? The first and the most important one is that we don't need any defrost cycle. I mean, the frost that is going to accumulated on the units, I saw many of them when they installed, they can reduce the performance of the heat pump actually, and then the heat pump needs to stop working, which means that stop providing heating and needs to go through a defrost cycle, and then after the defrost cycle can come back actually. But if we have a water source heat pump, so then we don't need to have any defrost cycle or any defrost control and system in it. Their efficiency is better compared to air because water can absorb or reject more heat because of its heat conductivity and heat capacity actually it has. And compressor also because of that, compressor life benefits from this one actually. This is also widely popular in residential application. There are a few ones, but those ones that they can have access to a well or to a water stream or to a lake, maybe that's a good one to consider if the codes and if the municipality allows that one. So then we can have these systems. Most commonly used water source heat pumps, they are closed loop water source heat pumps, which means that because the open loops one, the water from any water source that we have needs to come and then needs to be filtrated and then used and then go back. But in a closed loop, actually, we don't need to actually use the water source that we have. This is a typical water source or water to water heat pumps actually, because on the other side of it, we can have a hydronic system inside our buildings now. Instead of doing a duct work, now we can have a water pipe, which that water can be a chilled water or can be a hot water, so, provided to the building and then work that one. So again, we have a loop that going down to the water source that we have, and then either we have a blower or we can have connected to our hydronic system that we have actually. So this is again another picture of the fluid circuit of the water source, a heat pump inside that one, and again this reversing valve again exists here, and that's it. Typically for these kind of water source heat pump, it's better that to have a buffer tank actually, an expansion tank, which store a little bit amount of the water, either it's a hot water or chilled water, and then getting sent to the system that we have actually, and then we go from there. If we want to use open loop groundwater, so the temperature for the heating season should not go lower than 4 degrees Celsius, and for the summer season, the water temperature should not go above 32 degrees Celsius, because below or above these values, then the heat pump cannot operate at the COP that we have from the manufacturer actually. So the closed loop, that's a popular one. There are buildings that they can benefit from this one, and then this is good one. The ground source heat pump, we can have also two types of ground source heat pump. The ground source heat pump that we use the ground temperature, which is going to be soil. Across the GTA, I've worked on the projects. The temperature usually is between 8 to 10 degrees Celsius all year around, under the ground. And if we have a well or water source under the ground, maybe we can connect our closed loop to that one and exchange heat with that water source. So again, the ground and water source heat pumps can be used for our purposes as well. So efficiency of the water source heat pumps, the closed one, it's higher than the air source one actually, and they are good. And then we can have a ground loop like this, and then either is a horizontal or a vertical loop, and then we can extract the heat or we can reject the heat. That it depends on the season of operation that we are working with the heat pump actually. For
Sure,
larger,
yeah. Can
sure.
you explain a little bit what makes a ground source heat pump more efficient than an air
Yeah,
source?
Yeah, I mean there are two reasons. The first one is that we have a high capacity or high conductivity and high heat capacity either on the under the ground or the water that we use. I guess that I have a one slide that I compare air to water, and in that slide you will see that how much we are almost 25 times more on the heat conductivity of water compared to air actually. And the same for the heat capacity as well. So is 4 to 1. So the heat capacity of water is 4.2, and for water is almost 1. So it means that the amount of heat that water can absorb or reject inside itself, it's much higher than air. So that's why. The other reason, which is a smaller in amount, but is a defrost, because we need to run the defrost system. And then that's also another reason, is that that's the waste actually. We use electricity for defrosting, but we don't provide any heating. So that's another reason these water source heat pumps, they are more efficient actually. The same thing for the ground as well. The ground temperature across the GTA, the projects that I worked with, is that 8 to 10 degrees Celsius. Again, it's a constant temperature. But when outside is minus 10 degrees Celsius, so then the COP or efficiency of our heat pumps becomes lower actually. And that's why, again, the efficiency of our heat pump goes down. So that's the reason, is that because we depend on the outdoor weather on an air source heat pump versus the water source heat pump or ground source heat pump, typically they work with an almost constant temperature in the ground and a little bit of variation of the water source heat pumps actually.
Great. Thank you.
No problem. So for larger buildings, actually, the ground coupled or the closed loop heat pumps, they make more and more sense actually, because the installation cost of the ground source or water source heat pumps can be a little bit high for a one single residential family. So for a larger building like a condo and those kind of towers, it makes more sense actually. And then their system becomes much smaller. They need just the pumps and then a refrigerant that going to the ground and then bringing back the heat during the winter season or rejecting the heat during the summer season actually. We can add actually cooling towers to these ground coupled or closed loop heat pumps to increase the efficiency and also provide more support or supplement to the amount of heating to amount of cooling that we needed. If we require in extreme conditions, in extreme cold temperature, when for example, because we need to maintain the water temperature in the loop is 16 degrees Celsius. So then that's why we sometimes we need to add boiler for supplement and then make that heat pump that we have and a hybrid system. So then it can switch to use the boilers. But this is again in the times that outdoor temperature is, let's say, minus 25, minus 30 degrees Celsius. This is for those times that uh, we can run our boilers actually for heat. So the water to water heat pumps actually, they are capable of producing from 1.5, 1.7 to 54 degree Celsius of water temperature for any commercial, industrial, residential application, any of them. And then the good thing is that we can connect them directly to the hydronic system that we have, or any radiant heating, from the floor, or space heating using the fan coils, or even the ice and the snow removal that we want to have it for our ramps or whatever that we want to have it actually. So these are good application. I know that the capital cost is higher compared to the other systems, but again, it's good to be considered and evaluated for the projects that we are working on actually. So now let's switch to the hydronic heat pumps that we have. So hydronic heat pumps means that now on the inside of our buildings, we want to have a hydronic system. And using water or water-based solution is a good one actually to have for our heat pump. So this is really good to have it, because again, water is more efficient. So why using hydronic system inside our building? The first one is the control of air and surface temperature. That's a good one, because when we have a radiant system which connected to um, a water or hydronic, heating or cooling, it provides the heating in a very nice and we call it natural. I would call it almost near natural convection because the air moves close very uh, in a very low speed close to the radiant heater, and then gets heated and then moves, and then the room or wherever that we have it gets heated actually, versus the forced air system that we have. It blows a large amount of warm air at a certain amount of time, and then it turns off, and then when it goes again to a low temperature, it backs on and do the same thing. But that one provides a more comfort actually. They are energy, provide energy saving. Again, this is a hydronic system and inside the building, so it's better that we combine our heat pumps with these hydronic system. Actually, they can work on the low temperature that we wanted. They can reduce the loads, and they require less maintenance compared to the forced air actually. And these days, we can have a thermal metering because it's a water. For air, it's hard to measure actually. We need to flow rate and measure the temperature and so on. But for water pipes, even if we need to meter, and if we are talking about the multi-unit residential building, again, we can meter how much hot water we provided to each unit. And then, even for charging, for other purposes, we can have that one actually. This is the slide that I talked about it actually. So in this slide, what you can see actually, the specific heat capacity of water compared to air is 4 to 1. That's it. So water has 4 times more heat capacity than air. That's that we have. And if you look at the thermal conductivity of water is zero point 0.6 versus the air is 0.02 actually. So again, water is 25 times more thermal conductivity than air. I have one example here. For an 80 kilowatt heating and cooling that we have, with a temperature difference of just 2 degrees Celsius, we need to provide 33,000 liters of air per second. But for the same amount of heating and cooling within that temperature difference, we need to just provide 11 liters of water. So you see that the fan operation and the volume that we need to move versus the pump and the pipe size actually that we can have it. So that's it. That's the beauty of hydronic system. In Europe, I mean, most of the Europe, they use a hydronic system. It's a little bit more expensive compared to the forced air system that we use here in North America. Yes, the installation cost and the capital cost might be higher, but at the end of the day, it's much, much more efficient. And if you look at the life cycle, it works better actually. But let's go back to our, ground loop source heat pumps. So you see that we can have a condo tower like this, and then it can have in front of that, it can have in the parking lot, under the parking lot or wherever it is, we can have the loop actually going down, and then on the roof we can add also some cooling towers, so then it can be connected. And if we need extra heating sources for extreme cold weather, then we can add a boiler as well to our system. And then we can have the heat emitter, like these radiant system that exists. And we don't, sometimes we need a fan coil, or sometimes we don't need that one. So it works by the natural, convection actually. So the hydronic systems can be, classified or, based on these fossil fuel boilers and electrical thermal storage equipment, hydronic heat pumps, renewable, that solar thermal collector or solid fuel boilers as well. But today's discussion, we are talking about hydronic heat pumps. So, and then if we are having a ground source heat pump or water source heat pump, that's a great one to use inside our building. Also combine it with a hydronic system, and we go from there actually. Here I want to present some of the ideas about the electrification of the heating system and the typical retrofit opportunities. The first one that I want to start is that I know that the heat pump is here actually. So we want to go with a more efficient, system actually, and also it fits to here as well, which is a low emission. So heat pump works for both of these one, but this is an energy hierarchy. It's better and it's highly recommended. First of all, we do an audit and then analyze our building. And then the next step is that we avoid and reduce the energy waste, which we call them energy conservation. So, unplug appliances when we don't need them, actually use the natural lighting during the day when it exists, or close the blinds, during the cold nights, actually, and also during the summer, sunny days, so we don't let the sun comes in. So these are energy conservation. We turn off the light when we don't need it. That's the energy conservation, and it doesn't cost at all anything to anybody, actually. And then it reduces the demand and our energy cost. The next step after that is reusing or recovering the waste energy. So any kind of recovery ventilator or recovery system, it's highly recommended to be installed. So again, this will reduce the load of the heating and cooling and the size of the heating and cooling that we needed. This picture that you see here, this is on a condo tower, actually. The exhaust of all the washrooms is connected to these heat recovery heat pump, actually. And this is an interesting thing, is that it's a heat recovery heat pump. When the exhaust air that is going out wants to go out of the building, it extracts the heat from that one, and then bring it back either to the water system and so on. The next one is that now it's time to improve it and have an energy efficient equipment similar to the heat pump that we are discussing today. The other after that, it's now time to switch from the fossil fuel to low emission energy sources. Again, similar to the heat pump. If we cannot do anything about the systems that we have, and we did all of this from the top to the bottom, now we need to go either to offset, or we go with the conventional system that we have, actually. So this is an energy hierarchy that always, always, always we should remember that one, actually, and then try to reduce the load or demand, actually. But let's go back to our discussion about the residential buildings and how a heat pump can fit with that one, actually. So the heat pump can provide heating, cooling, domestic hot water, actually, for the entire building. So that's the one that we can have it. So you see on the left hand side, this is entire building, and we install only one heat pump, actually. And this heat pump can provide both hot water, domestic hot water that we need, actually. So it's connected to domestic hot water, and also it provides the space heating as well. So this is going to be, I would call it, centralized heat pump system that it serves the entire building, actually. Then we can move to the other side of the spectrum, which is going to be just individual room. And within that individual room, what we do is that we just provide air heat distribution or air cooling, actually, that we have. So we just install one maybe heat pump, and that heat pump actually serves only that room, or maybe each unit. For example, this one, which is each condo for itself, they have actually their own heat pump. That heat pump, similar to the centralized, actually, it actually serves as domestic hot water supply and also space heating or space cooling, actually. And then we can go, in between as well. So I want to take a look at these ones in details again. So these are the centralized, I would say, solution that exists for the entire building, and then we can have a different combination. These F that you can see here, this is an extra or supplement of the heating that needs to be provided. So these are if we need additional heating, then we can use, other sources of energy like a fuel or fossil fuel, and we can have those ones, actually. And then on the other side of the spectrum, we have heat pump for each individual room or for each individual apartments or condos, actually. And we can have any combinations that we want. We can maybe take out the domestic hot water, and domestic hot water, it has its own source of energy, actually. It can be anything, either fossil fuel or heat pump or electricity, but the space heating and cooling provided by the heat pump. So again, during our design, we need to consider all of these and then design based on this, because we shouldn't go just as the everybody else is doing. We need to consider that all of these options is available to us. Let's benefit from them, and let's design the one that is best and fit to our project actually. So now I have every of those situations in here actually. So for example, in solution one heat pump for all, this one, the benefit is very simple. It needs only one controller, and then all the distribution maintenance, everything is going to be easier. But the negative aspect is that high distribution losses, because we need a distribution both for domestic hot water and for space heating. So then the losses will be higher on that one. If, if we want to go to solution 1.2, one for heating and one for domestic hot water, so we have one heat pump for space heating and one heat pump for the domestic hot water. Actually, again, this is good. It's also, we can, for larger solution, this is good, and then we can have a phase approach, and then the Legionella prevention, which is a very very dangerous actually. So this solution might be better in that one, because now we have a separate heat pump, because there are sometimes that we don't need the space heating, but the domestic hot water needs to run. So then the Legionella can grow actually in those situations, because the temperature based on ASHRAE standard, it should be above 57 to 60 degrees Celsius to prevent Legionella to grow inside the warm water. So Legionella is a very strong bacteria, and it can survive at to that hot temperature actually. But the negative aspect of this solution is that high distribution losses again, and maybe some kind of a uh, uh, impact on the control and other aspects of that one actually. The next solution that we have is a heat pump for heating and other devices for domestic hot water. That other devices can be a fuel or whatever. So again, the heat pump is just for heating and for cooling purposes, and we don't use it for anything else. And then domestic hot water is actually provided by another type of energy sources. So it's not electricity, it's not a heat pump. So this might be good in some sense, but again, the negative part of it is that, again, we are going to have a partial use of fossil fuel for these cases. And then we can go to to other solutions like 1.4 heat pump for domestic hot water, and then for heating purposes we use a fossil fuel, which is not the case that we want to have it in our today's discussion actually. The goal is that once I show all these options to you, is that we review and we understand and evaluate each of these options for our systems actually. So for example, 3.3, this is the solution for the condo towers actually. So we group all the condo towers together, and then we have a heat pump with some kind of supplement actually for that one. And then we go, this is also a good solution for a large building, but again, distribution of this energy throughout the building, that's the problem. And also these decentral systems, they are noisy, and some people, they don't prefer them actually to have them. So again, that is also possible. And then because it's going to be a large system and it can be noisy, so then the people, they might not like it. Or we can have each individual apartments like this one. So we have European countries like Germany, Netherlands, they use these systems actually for their condo towers actually. So they have one heat pump that provides both for domestic hot water and space heating and space cooling actually. Again, that's a good one. Or we can separate if we can decentralize systems, so then we can separate and we go from there actually. Okay, now let's change the topic, and let's see that if we want to do a heat pump retrofit, and basically we want to install a heat pump or consider it for our building design actually, what are the steps actually? So these are the steps that typically, that for every project, that it's better that or it's recommended that we follow. We do a preliminary assessment. Basically, I would call it a backup napkin calculations, and then we do an investigation. Then we go for financing and procurement, and the source of money or any rebates or anything is available. Then we implement, install the heat pump. And then after that, it's better that we do a post retrofit and check that everything that we did is okay and working as is intended actually for our project. So in the preliminary phase, it's better that we pre-qualify our building based on the property characteristics and the design that I showed you before, for example. Then we need to assess the business case, and look at it. There are many assessment tools for the heat pumps these days. For example, TAF has a Toronto Atmospheric, Fund. They have some kind of application. It's a very simple application, but it's good to be used. And then it just, a couple of minutes work. It gives us some idea that, is this a good system or it's not, or I should choose a more efficient one. Then we need to go the investigation and do a financial feasibility of retrofitting with the heat pump to see that, okay, now does it make sense to have, the heat pump or not, and doing the dollar calculations basically. After that, we go and then we select the project. I will show you later on that always during this phase, we need to look at least 3, 4 options, 3, 4 brands of the heat pumps as well. So it's not just one supplier and we go with there and then that's it. No, we have to look at every of them because they are different from each other. Their performance, their efficiency, and their cost actually might be different. So it's better that to take a look, see that if there are incentive or rebates available, we apply for them, and then we purchase, and then at the same time we look at how we are going to assess this project after we installed the heat pumps actually. So then we go to the design and then, adding or, construction or implementing that heat pump uh, addition to our buildings, and then, verify the project is complete. We do the commissioning that we say that, yeah, the heat pump works, can provide heating, can provide cooling. And if it's connected, for example, to domestic hot water, also, it can do that one as well. And then we go back and do that one. But again, all these steps that I told you depends on the size of the project and the size. So if you are talking about a single detached house, actually, so maybe some of these steps needs to be tailored and just become light actually in terms of doing it. Some of them for the large buildings, like a large condo towers, it makes sense that to go each of them step by step actually. This is the one that I told you actually. So if you're going, either you're a single detached house owner or a townhouse owner, or you are designing or having a condo tower, again, it's better that to take a look at different options, option A, option B, option C, for example, option D, and look at all of these parameters. So these specification summary worksheet available on the natural resources website. Uh, and then you can download it and you can ask your contractor actually filled in these ones, and then you can basically compare options and to options and see that which one is a better fit for your facility or for your building actually, because it's really really important to take a look at all of these things. So there are many variables. I know that sometimes it's uh, it's it's over, but over the knowledge that everyone might have. But it's really important that when we hire a contractor, we ask them from day one that I need this one to be filled and completed and provided to me actually. Now, I said all the good things actually about the heat pump from the beginning of this session: energy efficient, low emission, and it's good to be coupled, for example, to an hydronic indoor system and so on. So all of them are almost listed here. So, increase asset value, reduce maintenance, it's a long-term investment, it's an energy independent, and it's cost saving. This cost saving, I have some slides I will show you what does it mean. This is a life cycle cost saving actually. There might be some government incentive, and they are energy efficient and they are environmentally sustainable. But what are the barriers of these systems? So the barriers are the initial cost. They are more expensive. They are more expensive than the other systems that are available. So it's not the cost, the initial cost that we need to pay is higher. The other reason is the lack of awareness. In the market, still there are some rumors, there are some myths that they talk about it. And because some people, they don't have a knowledge about it, they are a little bit against about it. So that's not good. So we need to raise the awareness, and we need to bring this information to everyone, and everyone understand that one. The other one is the perceived reliability issues. Again, that's another concern that exists. The technical challenges that the people, they are used to these systems that you're using. They think that, oh, this is going to be a new things, and then new technical challenges. Or space requirement, that can be another barrier, because we cannot put these heat pumps on the ground similar to AC that we have it actually for detached houses. It needs to be in a raised, it should be at least above the snow level that we get actually. So then the snow does not get into the heat pump. And also, if we can have some kind of a cover at the top, also it's good that the rain or the snow also does not getting accumulated over the unit as well. So again, it requires a special space to be designed for this one. Then related to the initial cost is access to financing, and incentives that are available. Sometimes is available to the people, sometimes they are not available actually. So the high upfront and operational cost, that's the barrier that everybody is talking about, this one. But again, the operational cost, yes, the electricity is more expensive than natural gas, but I will show you later on the natural gas also is becoming more expensive, and that's why the cost becomes comparable to this one. The functionality, concern is that they say that we live in a cold climate, and this cold climate, it's not, these heat pump doesn't work, but no, these heat pumps, they are good actually, they're working. Some people, they are, have a concern about the noise level. Yeah, but the noise level, consider that one when we run our systems. So when we run our furnace inside a single detached houses, so there is a noise because of the combustion, and then that's the one that we need to have it. But now the noise will go outside of the building. So again, that might not be a big concern actually. The complex, customer journey and some kind of status quo bias that exists that I talked about it, because the people, they don't have a knowledge, so they are a little bit against these systems actually. Some tenant consideration as well. So we might think of the disruption because of the installation and the changes in their utility bill for the tenants. Again, that's another impact, but we need to notify them, we need to inform them, and we need to basically let them know that now this is a better solution, this is more efficient solution in a long run actually. There are some concern about the incompatibility with the current heating system. Again, that's a fear that exists, but this is not true things. If we hire a contractor who is licensed and who knows these systems, they can actually make the systems combine together and make a hybrid system for us actually. Difficulty on estimating energy efficiency, but this is not, I showed you that, it's not that there are lots of studies showing that the heat pumps are more efficient. I showed in that example that actually the heat pumps are more efficient in a simple, very simple way, actually. This is also true time consuming quotations, because proper sizing and selection can be sometimes difficult. And that form that I showed you, that considering 4 options, and then each option telling me that what is the COP, what is SEER, what is EER, what is the heating supply, and so on. So it can be time consuming, but again, that can be another barrier for the building owners. We need to make these things easier for the building owners, and this is the job of our contractors, that they do that one, you know, to make this one easier for them actually. Uh, Sometimes, it can be difficult and overwhelming to keep up with with the pace of change. Actually, so that's the thing that it's happening, in a digital world, and this is also the thing that it's time that we switch to a better and more efficient systems. Actually, similar to the cars and other things that we do. So this is the same thing. We don't want to use an old, printer that we had it, it was dotted printers, and it was took a long time to print, or the computers, the same thing. So this is the same thing for heating and cooling systems within our buildings. We need to do this change, and we need to go toward a more efficient systems actually. Now I want to talk a little bit about the sizing of the heat pump and how in a simple way that how we do the heat pump sizing actually, and talking about the supplement heat, do we need it or we don't need it actually. So the most important item in a heat pump sizing is a thermal balance point. This is the point that this is the point actually that the heat losses through our building envelope actually becomes equal to the amount of heating that is getting supplied by the heat pump actually. So this is the balance point that we needed for our house, and the contractor that we bring actually, they need to do these calculations for us, and they need to tell us that, okay, yeah, this is the right size for your building actually, or for your unit, or for your system, that facility that you have. So finding this balance point based on different options that we talked about it, it's a very critical step in finding the right heat pump for our facility actually. This balance point also will tell us that, do we need a supplemental heat for our building, or we don't need any additional heating sources as well. Do I need to keep my existing furnace, or having some extra heating systems for those days that are extremely cold, and how much should be the size of that one? Again, this comes from here. So this is the graph that I have, is that I want to show you. So this blue line that you see here, this blue line shows the heat loss through our building actually. So this is the heat loss when we have a different temperature, but when we have a different outdoor temperature actually. So this is the heat loss that we get. Um, these heat losses can be when it's 18 degrees Celsius. That's typically, our building doesn't lose any heat actually. When it's 0 degrees Celsius actually, so our building envelope, which is windows, walls, doors, roof, and the foundation, they lose heat actually. So that's the amount of heat that we are losing. So it's plotted in here. And when it's minus 15 degrees Celsius, so the building, for example, loses this much, 60,000 BTU per hour, which is almost equal to 17 or 18 kilowatt actually. So this is the amount of heat loss that we have for our building when outdoor temperature is minus 15 degrees Celsius. Now, if we look at the red line presents the heat pump operation actually. So this shows that when it's minus 15 outside, then the heat pump operates, can provide this much heat actually. Let's say 25,000 BTU per hour, or almost 7 to 8 kilowatt actually. So it can provide that one. And then we see that there is a big difference between the amount of heat that my building needs, 60,000 BTU per hour, or 17 or 18 kilowatt. What the heat pump can supply is 25,000 BTU per hour, which is almost equal to 7 to 8 kilowatt. So means that I need uh, 10 kilowatt extra heating to be supplied for my building actually. So this shows us that how much supplement heat or auxiliary heat or additional heat needs to be supplied by extra sources that we need to bring the building. So this is the point. This line, this is for one type of heat pump. We can buy a heat pump that goes like this. We can buy a heat pump that can go like this. So the line for each manufacturer and for each model of the heat pump can be different, which means that it might reduces actually the amount of supplement heat that we require for our building. Each heat pump, now getting a little bit into the details, each manufacturer provides their heating performance actually. So they provide the heating performance, for example, at 1,000 CFM, indoor air volume, and how much BTU we get. So when they say there's minus 20 outside, it just can provide you almost 6,000 BTU per hour actually. So it's around 5 kilowatt, something like that actually. So that's the one that, and then this depends also on our building envelope. Do we have, as per today's code, our building envelope, or our building, let's say, is 40 years old or 60 years old actually, and the building envelope is not, holding the heat, and then it's emitting heat out actually to outdoor. So this is the balance point again that, the contractor, when they come and they design the heat pump or they size the heat pump for your facility, they have to do, and they have to show you that how much extra heat at different outdoor temperature is needed. And then based on that location, that city actually, they have to choose the right. For example, in Toronto, let's say the coldest recorded temperature over average over the 30 years is between minus 18 to minus 22 degrees Celsius, for example. So this is the temperature that we need to consider for the sizing of any heat pump for the GTA area. For the other regions of Ontario, it can be different, and we can consult with the ASHRAE or Natural Resources Canada website and get those weather data from there, those extreme data. So when they come, they look at different heating or heat pumps for our system. Basically, they should provide us a graph similar to this. On the right-hand side, we don't have any problem because that's it for cooling. And these heat pumps, usually they are sized for heating, not for cooling, because we live in a cold climate. So they have to size it based on the heating. When they size it for the heating, you will see later in the next slide that I will talk about it. Usually they go oversize actually. So oversize on the cooling, so means that we have a little bit or slightly over the cooling that the building needs actually. So then means that it's oversized and it can provide a lot of cooling to our buildings. But this is again the heat load line for the building, and then these are different types of the heat pump that exist, and then the balance point for each of them, and then the contractor should recommend which of them is the best for our facility or for our building actually. These are not written on the books and say everybody should follow that one, but these are recommended based on the industry best practices actually. So basically in winters, when we have in the regions that the winters are less extreme, the cooling capacity basically will be oversized by the 15%. So for areas like Windsor, Toronto areas, these are I mean, they are not very extreme cold in a winter season. So the heat pump can be on the cooling side, can be oversized by 15%. But if we go to the northern part of Ontario, so then the winters can become extreme, then we are allowed actually to oversize the cooling by 25%. So it's okay. But again, in those cases, most of the time, we need a supplemental heat to be provided for those extreme cold days actually.
Sorry, I just wanted to call
Sure.
attention quickly to the time.
Yeah,
Um,
sure.
we've got about 20 minutes left.
Yes, I will a little bit speed up on this one, but now we are finishing these technical stuff, and then thanks for reminding that, Megan.
No problem.
Thank you. So now there are many approaches these days. I want to bring your attention from the manufacturer side that, they either add multiple compressors, they can add two compressors. This is a very typical for these days heat pumps that we want to buy. They have two-speed compressor, or it can be a little bit more expensive, variable speed compressors and motors, and then some kind of unloading. So these are the technologies that getting added actually to the heat pumps and then make the heat pumps actually more efficient. So now using a, a better refrigerant or the refrigerant that has a lower boiling point. So that's these are the changes that the manufacturer, when they see the demand of the heat pump, so they do that one actually. So again, this is a graph that available from Natural Resources Canada, and it shows that the fractional, the annual heating above the outdoor temperature that we need, because that's the one that we want. And then how much is it for every climate that we have? For example, we are in the southern part of Ontario, or we go to the northern part of Ontario. So basically, in Ontario, we have three different climates actually, and we can choose based on those thermal balance point that I talked about. Then we go to the control strategy. Again, the control strategy becomes important. If we need a supplemental or auxiliary heat, then the control strategy becomes a big component, that how the contractor or the trades that they come and install, they set up that control. Where is the point that the heat pump should be turned off, and my our auxiliary system for the heating should start actually. So that's the control system that becomes important. And then they should have similar to this, decision matrix. They have that one, and they set it up on the both heat pump and the other system, the other auxiliary heating system that we have actually. So, the total supplemental heat should not exceed the home's heat loss at the design conditions by more than 15%. We talked about it, and that's a typical based on the industry. That's the industry and the trades or contractors, they follow this rule when they do that one. And also for, the same decision matrix for the backup heating when it's needed to be supplied. So this is the graph that I told you before. Again, these are the heat pumps with different efficiency of COP1 up to the COP of 6, which is more expensive one for sure. But again, the balance point can become different, and then we can have, less extra heating or auxiliary heating for our facility actually. I want to, the outdoor thermostat also needs to be set actually. For example, for these temperatures that we have for summer and for winter, this is also has an impact on the COP and operation of the heat pump based on our. And usually the trades or contractors, they consider a safety margin of error when they set up for that one, and based on the balance point and the calculation of the output of the heating that we have from the heat pump. I will go very quickly over the terminologies that you might hear about the heat pumps. The one of them is, which is really important, is the coefficient of performance, or we call it COP actually. So COP is the amount of that heat that is delivered by the heat pump and divided by the amount of electricity that we put into the system actually. So basically the amount of heat that we remove during the summer, or the amount of heat that we supply to the building, that's the output that we have, divided by the amount of electricity that heat pump use. That's going to be the COP. There is another uh, metric that we can take a look, is the energy efficiency ratio, EER. This is just about the cooling. So the cooling capacity that our heat pump can have divided by the electricity that we put into our heat pump actually. Then we go to another similar to EER, we have HSPF, heating seasonal performance factor. Again, this is the total heating provided to our building divided by the amount of electricity that our heat pump actually used. And then this, again, HSPF can be different from the different models and different manufacturers. The other one, we have a seasonal energy efficiency rating. Again, this is a measure of the heat pump's, again, cooling efficiency over an entire season. So this is similar to what we had for the EER actually, but this is the seasonal one actually. So the work done by heat pump requires all of these. So indoor coil typically sometimes needs to become larger. The indoor air volume maybe becomes greater because the heat pump needs to work a little bit more, and then greater care must be taken for during the managing the flood back and those kind of. But these are the things that, again, on the contractor that we hire, and that we ask them to come and they to design or basically size the heat pump for our facility. After this, I want to look at some case study, information that are available, and then let's take a look at what's happening, if we install a heat pump versus other, types of heating that we have. So in this left-hand side graph, if we consider a conventional electric heating, the annual kilowatt hour that is required in that case study is almost 6,000 kilowatt hour. For the same building, if we install an air source heat pump, it becomes almost 2,000 kilowatt hour per year, actually. And if we go down to a ground source heat pump, then the efficiency is much higher, and then it requires almost 1,500 kilowatt hour of energy per year. So that's the one that we have. And if you on here, I have annual average space heating energy use that we have, and the forecast of the electricity rate for the residential sector. So we are almost here right now, almost 21, 22 cents per kilowatt hour. As per the data that published by TAF, we see that the electricity price might go up to 26 cents actually per kilowatt hour almost after 2030 or near 2035. That's the plan. But let's look at a combustion heating, which is very typical getting used in our buildings right now. So their efficiency these days are 80 to 98%. So they are good ones. The energy cost is 45 cents uh, per cubic meter. And if we have a resistance heating, that also it will cost us 15 cents, let's say, per kilowatt hour on average. And if we install a heat pump with a COP at typical COP of 2.5 to 4, it's going to cost us $10 per gigajoule and then up to 20. I This row is the better one to compare because they have a different unit, so we cannot compare. But let's look at here. If we want to run our combustion heating system, it's going to cost us $15 per each gigajoule. If we run our resistance heating, it's going to cost us $41 per gigajoule. And the heat pump is going to cost us $10 up to $20 per gigajoule. So now we can compare basically the heat pump with the combustion heating system that we have. If we add the carbon tax to our calculation, let's say it's going to go up by 2030 up to $170 per each ton of CO2, then these combustion heating system becomes comparable to the heat pump actually. So this is an interesting fact to see that, yeah, a couple of years later from now, then the heat pump energy cost actually, or operational energy cost, becomes comparable to combustion system. That's a one concern that people they have today. If you look at the emission of a combustion system is a 49 kilogram per each gigajoule of energy used, versus look at heat pump is 2 to 4 kilogram of CO2 per each gigajoule. So you see that it's much, much less, than the combustion system that we have. The same thing, again, in this graph shows that one, but in a different format, shows that if we consider those numbers, again, that's gonna increase, and then the price of the running a heat pump becomes almost equal to a combustion system, actually. I have one example in here because the temperature difference of the residential building, if we run a combustion system actually, so we require a higher temperature difference. So that's why we at the end of the day we require a less amount of airflow that coming to our building. But when we have a heat pump, the heat pump, because of its capacity and the temperature rise, the temperature variance that we have, so then we require almost double of the CFM of the air that we have. So that's why you need to be careful when the contractor comes. They need to take a look at that one and doing the calculations for you as well. Now, I want to talk about the climate change. This is a reality. We cannot, ignore it. This is based on the science. This is coming from the Natural Resources Canada, the study that has been done. Right now in the southern part of Ontario, we are, based on ASHRAE, we are in a climate zone 5. And then a little bit we travel north, becomes climate zone 6 and 7 actually A. By the end of this century, actually, our climate becomes closer, in southern part of Ontario, like the Toronto area, will become similar to Vancouver temperatures, actually. So this is a climate change. And there is some kind of a good news with regard to the heat pump. The good news is that if we install a heat pump, then we don't need to be worried about the sizing of the heat pump for that time, because those extra heating that we needed because of the climate change, maybe we don't need it. But the cooling, we said that we are going to oversize the cooling because of the heating purposes. At that time, we need a cooling, extra cooling. Again, that's the climate change that we see. So that's the fact, and it's happening. This is the science that they did the modeling, the weather and the future, and it's coming and it's happening. So we need to prepare our buildings that they are going to last for a long time. So we have to prepare from now, actually. So I have a case study that I want to go through that one, and it's comparing actually the air source heat pump in different buildings actually, and then looking at the COP of the heat pumps and the refrigerant for the low boiling point that is coming, which is called cold climate heat pumps, air source heat pumps that is coming to the market or is available right now to the market. So in this study, what I have is actually they did, they look at the weather file, different years actually, and they try to look at different cities or different within different, provinces. Toronto from Ontario was selected. So this is the building that we have. So it's, the condition area is around 188 square meter, and the size of that one actually. And then these are the climate zone that we are talking about and the typical building envelope, R value that we have. And also they looked at the actual equipments, the actual heat pump that exists in the market, and they look at it, their COP, for example, their COP, look at this brand. I'm not saying that this brand is the best brand, but look at just the difference between the COP. So we have a range of, let's say, 3.6 up to 4.4 actually. So for the cooling purposes, and if you look at the heating side again, we have, let's say, 2.78. That's the heating COP that we get, typical heat COP that we get, and it can go up to 3.8 actually. So these are the actual equipments that are available to the market. They looked at it in this study, and they looked at the heating demand, the peak heating demand for different climates that is happening. So you see that for sure, because the climate is changing, so the heating demand is going down and down actually. So they expect that if from 98 to 2014, we needed 16.4 kilowatt for our peak heat demand. In, let's say, 2030 up to 2040, we need 15. And if we go after that, we need only 13 and a half. So this is the climate change, and this is the peak demand that is happening. The impact of the heat demand is that this is the extra heating or supplemental heating that we needed to provide in the beginning for the Toronto building actually, but after that we need a less amount of extra heating supplied by, extra sources than the heat pump actually. So the GHG emissions of each of these compared to the baseline model. So the baseline model that we have, they use, typical conventional systems that we have, and then compare them actually with the different brands and how much is the GHG emission. So you see that almost half of any of these GHG emissions is going to happen actually. So now the cost of heat pumps, for sure, it's a very important, and the capital cost of the heat pump. So in this case study, I want to take a look at that one and see that if we have a conventional system, which is a gas, burning combustion system plus an air conditioning, and then on the other side I have a heat pump, either is, backed up with a gas or backed up with electricity, how we are going to see the numbers. And then the new cold climate, or they call it CC air source heat pump, CCASHP. So those are also available. They are for sure more expensive, but again, those are very efficient in our climate. So this graph shows the cost competitiveness. This includes the total cost, the capital cost plus the operational cost for the buildings across the Canadas actually. So they did the modeling based on that one, and anything below this green line shows us that, yeah, this is the amount of money that the building owners, they are going to save actually. So the residential building owners, they are going to save this much per year actually. And any dots above means that the conventional system still is better to be used. So look at here, we have a single detached home for Toronto area, and look at Toronto area. This line this almost yellow line that I highlighted is the line for the conventional system, and the green vertical line is about the standard heat pump backed up with an electric heater actually. So this is the system that you see that it will cost the building owner, a single detached house owner actually less. If we look at the same thing for the for the other types of the heat pumps, again we can see that one, but this is for the buildings that are built last year based on the code that we have last year. So we see that the difference becomes a little bit less, but again the heat pump is the winner, and the owner of the building in through the long term can save energy actually. And this is an annualized cost for cost difference between a heat pump and the gas heating, similar to the graph that I showed you. This is for the Toronto area. So it shows that in most of the time, the heat pump works better actually. These are the assumptions that we have for the initial cost. So if you look at these table, you see that they consider everything. The panel upgrade that is needed from 100 amps, for example, to 200 amps that we need to do that one. If we need to do a ducting or extra ducting and so on. So they consider everything in their study. So it's a very detailed study actually. The final slides that I have is some tips finding and working with the contractor. So for sure, the contractor should be licensed and should be trained professional that they work on this one. Natural Resources Canada website has, a good document. And for sure, we need to do some kind of preliminary investigative interview with those ones and to see that do they understand what they're doing and what they are going to provide when they're going to do the sizing actually. And it's a best practice to follow the manufacturer recommendation and also the building codes that exist within our province in Ontario, actually. And looking at the equipment performance should be verified and based on the published data that they have it. So it's better that we take a look at that one. And the job site also very important where we want to install the heat pump actually. So that was my last slide. And then welcome any questions.
Thanks, Shariar. Was a lot of information covered today. We do have one question that came in a bit earlier when you were talking about the water to water systems. I decided to save it for the end, but the question is, for an older building with traditional cast iron radiators, using water to water heat pumps to replace the existing boilers, how would you get that last 20 to 30 degrees of heating? Or would you instead try to replace the existing radiators with higher flow, lower temperature models?
The person that's actually answered. So for sure, those cast iron radiator needs to be installed because the efficiency of the radiation of those materials that was used at that time was not good. So it's better that we replace it with the new radiators. They are more efficient. The number of fins are more actually, and then they are also compact in the size as well. And also the flow rate that we needed, as you mentioned, that we need to provide a different flow rate compared to the boiler that exists in that system.
Thank you. Okay, we've got 1 minute left. If anybody wants to raise their hand to ask a question, we can do that. Otherwise, do you mind just going to the next slide as well, Shariar?
Yes,
and
sure.
I will talk a little bit about some extra tools and resources. So we do have some virtual one-on-one coaching. We have an intake support forum. You can also email us. Our email will be on the final slide. You can sign up for our monthly bulletin, get updates on new training events that we're hosting, as well as tools and resources. There's a live training calendar for these Save on Energy workshops, and of course, the training and support webpage at Save on Energy, which I did put in the chat earlier. Here is one more question for you, Shariar. If considering a cold climate heat pump for a new build, multi-unit dwelling, about 1,000 square foot per dwelling in the GTA, do you think that supplementary heating is needed at all beyond, say, in a common area?
I don't think so. That needs to be sized, but the balance point needs to be calculated based on the envelope, RSI of the windows and walls and everything. But if it's a typical answer that I would say that a CCASHP, cold climate air source heat pumps, they don't typically require, they do not need any extra heating actually. And a little bit of extra heating can be supplied by a backup, resistive electric heater. That's the one that I can say. But again, that's not the answer, is not a correct answer because it needs to be sized for your facility based on the size, the envelope, and everything else.
Awesome. Thanks so much. I want to thank everybody again for joining us today. I had a great time. And please do reach out if you have any questions. Our email is up on this final slide. The link to the training and support webpage and a QR code to sign up for Save on Energy's quarterly business newsletter, which is separate from the training and support team. So thanks once again and have a great day, everybody.
Thank you, everyone.